Okay.
That's a quiz question. Just right there.
All right. So, we're going to write parametric equations for the line through these 2 points. Now, I want to go back to something we talked about yesterday. Yesterday, we had a problem that looked like this. Those are parametric equations. We put that in Cartesian form, and it was a line. You remember that from yesterday? So now we're kind of going the opposite direction. We have been given 2 points, and we need to write the parametric equations of the line. Now, who remembers anything from yesterday? Sammy?
1 and a 2 is a point on the line.
So this is some random point on the line. Okay, perfect. Not anything important, just a point on the line. Miss McCauley?
The coefficients next to the t are the slope.
Are the slope of the line. Remembering that it's y over x, right? So we could actually write the equation of this line parametrically. Okay, you got 2 points. I don't care which one you pick. Let's just use the first one. So we'll put -2 for the x and 3 for the y, because remember, we noticed this yesterday. This is a point on the line. Okay? Now, what is the slope here? What is the change in y?
5, 3,
1. Y is 3. So I'm going to say 3t. That's how y is changing in steps of 3. And how is x changing? In steps of 5. Now, there are infinitely many answers to this question. Remember in the beginning, I picked that point. Could I have picked this point? Yep. When I found slope, I don't know how you, when I found slope, I did 6 minus 3, so I got +3. I could have done 3 minus 6 and get -3. These are both acceptable answers. There are many acceptable answers. How many points are on a line? Infinitely, a lot, right, a lot. So it makes sense to either use this one or this one, because we know them. But are there other points we could be using? Sure, if you want to mess around figuring that out. Could this, instead of being 5 and 3, and 5 and 3 is what makes sense. So I would imagine that's what most of you are going to come up with. But what if you put 10 and 6? Would that accomplish the same thing? Yeah. So what I'm trying to get you to see is there are lots and lots of different ways to answer this question. The idea is that right there is a point on the line, any point, and this right here, y over x, represents the slope of the line. Lucy's your hand up?
You answered my question.
Okay. All right, everybody okay with that? That was easy. All right, now, what happens to this problem? Let me go back to our original answer that we got. This is the answer that kind of makes the most sense. What happens if I restrict my t values between 0 and 1? So here, my implication was t was infinite. T was everything. And that's going to generate this line, whatever it looks like. Okay? What happens if I take the same equations, but I restrict those t's? What do you think happens? Well, what happens if I let t be 0? What do I get if I let t be 0? Point -2, 3. And what happens if I let t be 1? And t can be anything in between those two, right? but not beyond them, just in between them. So when I let t be anything, I got the entire line. When I restrict my t's, what do I end up getting? A segment. And when it's 0 to 1, it's going to be the segment joining the 2 points that you created. Okay? If it, as long as this is in simplified reduced form, which it is. If I let t go from 0 to 2, then I would end up out here. Does that make sense to you? And I can just make my segment as long as I want by extending t. Okay, all right. We're a little behind, so I'm gonna skip 6, but I wanna do 7, all right? So number 7 says, a distress flare is shot straight up from the ship's bridge, 75 feet above the water with an initial velocity of 76 feet per second. Now stop right there. Does that sound like any problems we've ever done in our lives?
Yeah.
It sure does. It sounds like projectile motion. Anybody remember the projectile motion setup? Negative 16t squared. Okay, what else? Anybody remember? Plus, in this problem, it would be 76t, because what goes here in this spot? In the formula, it's v sub naught, which is the initial velocity. And anybody know what goes on the end? It would be the 75, because in the formula, that is the initial height. Remember that now? When we're measuring in feet, it's always negative 16 here. That's the gravitational feet deal. Okay, so here's my equation for this problem. All right, now what I'm supposed to do is simulate the fluid motion. So what I'm supposed to do is set this up parametrically. Well, this is my y, because in this equation, what does the y represent? The height, right? What does my x represent? The time. So I'm going to let x be t. And there are my parametric equations. Okay, so let's graph this and see what it looks like. What do you think it's going to look like? Oh yeah, it's going to be better be a parabola, right? So make sure, I don't know who's used your calculator, make sure you are in parametric mode, and then type in y equals, and x is t, and y is negative 16t squared plus 76t plus 75. Okay, now I need to do some adjustments with my window. Any thoughts on a t value? I think I'll just use 0 to 10 to start off. Remember, t is the time for me, and I'm shooting a ball or something up in the air and it's coming down. It's not going to be up there very long, so I think that'll be good enough. Okay, and since x is t, I'm going to make x match that, so x is going to be 0 to 10. And then my y minimum, I'm going to go ahead and leave that 0. What do you think I should do with my y max? Now remember, y is the height. So I don't know how high this thing's going to end up going, but it's going to be bigger than 75, right? So let's try 200. And I just picked that. If it's not big enough, you know what to do. Hit graph. Did it do what you thought it would do? Yep, the ball went up and it came back down. Now, here's what I'd like you to do. I'd like you to press your trace button. Okay, we haven't used our trace button very much, but press your trace button and then use your arrow to watch the ball. Are you watching it go up? And then it's going to come back down. We have used the calc capability of our calculator to find maximums and zeros and all that. Your trace thing, when you use the actual trace button, you can watch the ball go up and down. Okay, well that was easy. All right, let's try the next one. Number 8.
What about like where it says simulate the flare condition?
I didn't put the lengths of time in there, so I did it from 0 to 10. If we did from 0 to 1, then we would see only this little piece of the curve. And then from 1 to 2, we'd see the next piece and so on. Yeah, I just didn't put all those little pieces in. And forgot to take that part of the question out. All right, Kevin hits the baseball at 3 feet above the ground with an initial speed of 150 feet per second at an angle of 18 degrees with horizontal. Will the ball clear a 20-foot wall that is 400 feet away? All right, this one's a little bit trickier, but I think maybe we can figure it out. The velocity or the magnitude of the vector, the magnitude of the velocity vector is 150, and the angle is 18 degrees. So would you agree with me, let's back up, would you agree with me that the components of the vector, that this is the velocity vector, the components of the velocity vector are 150 cosine 18 and 150 sine 18. Would you agree that those are the components of the velocity vector? Yes. Yes. One thing you were supposed to have learned in those first 2 sections of the chapter is x is magnitude cosine, y is magnitude sine. Just like the wind in the airplane. All right, how can I use that in my parametric equations? Anybody have an idea how those could be used? Sydney?
Well, are you solving for? I guess you can set it equal to whatever your y is gonna be on that side and your x on that side.
Okay, you're exactly right for this one. 150 cosine 18 t. That is x. Now we gotta be careful with y because y is height, and isn't this baseball like a projectile going up into the air? So we're gonna start with our same old negative 16 t squared thing. But that initial velocity, now we're gonna put in the y component of the initial velocity. So this is gonna be 150 sine 18 t. And then plus, well, how high was the ball? 3. So Sydney is right on target. She says, won't your x be that x? Yes, x is varying over time, so it's this times t, 1 second, 2 seconds, whatever. And then for y, we have to have the projectile motion format. This is the velocity piece of the equation, so we'll stick the y piece of the velocity in there. Perfect. All right, let's graph that. Now, this one is tricky to type in. Caution. Sometimes I have issues with this. I have to be really careful because the calculator is going to automatically put parentheses there. So you got to start with parentheses, 150 cosine 18, close both sets of parentheses, and then put your t. And the same thing's going to happen here. These are tricky to type in, so please take your time. And get it typed in right.
understand that first. What's your window?
All right, now we need to, excuse me, we need to talk about our window now. Who are my baseball players in here? Somebody's played baseball before. How long does it take the ball, like if I hit the ball, how long does it take it? Not very long, right? So maybe we let T go from 0 to 4 seconds. Now, what about X? Well, where's the fence I'm trying to hit? How far away is the fence? So I gotta make X bigger than that. Let's make it 450. So 0 to 450. Okay? Now, what's Y? 0 to something? 20? No, wait. Is 20 the height of the fence? Yeah, it's gotta be more than that. Let's make it, this ball might go high. Let's make it like 80. Okay? So set your window where they say 0 to 4. Now, we may have to adjust this. What am I making? What did I say? 80? Oh, actually, those numbers all worked. Did you see a nice little parabola?
What is changing the T value? Because I don't see a difference.
What?
When I change the T window.
Oh, well, we can only see the part of the curve when the ball's in the air. So after the ball hits the ground, there won't be any more picture. All right? I mean, it won't be an additional picture, I mean. Okay, hit trace. Here's the question, guys. We could do this algebraically, but hit trace and watch your ball. Are you watching it go? Yeah. Now, how high is the fence? The fence is 20 feet tall, right? So when the ball, I'm just tracing, and when the ball is 19 feet above the ground, I'm only at 354.8 feet. Where is that fence? How far away? 400. Is this gonna clear the fence?
Oh, yeah.
No, not even close, right? Not even close. You can watch that through trace. We can do it algebraically, but we can also do it by tracing. Tess?
So what do you click on trace? So say hit trace and then.
No, not second trace, just hit trace. And then use your arrow buttons to watch the cursor. And when the cursor is 20 feet above the ground, you gotta see it, you're 400 feet away, and you're not. So the ball is gonna come down before it hits the fence.
Okay.
Lucy, is Y the height
Oh,
of
because
the
at
fence?
400 feet. Oh, it doesn't clear it. I see what happened.
Yes.
Because it's 400 feet long, so then about 400.
Okay,
Yeah, it's not clear. Okay.
all right, so
That's
if
actually even caught me out.
you have not had a chance to play around with your trace button, it's very, very useful for kind of general type questions like, is the ball gonna clear the fence? You can tell from trace it's not. If you have to find anything specific, like when is it 20 feet above the ground exactly, then you have to do that algebraically, which we did before, like with second calc intersect. Graphed 20 feet and looked where they intersected. But trace can be really useful for general type things. Tess?
So, I'm curious, how do you know that it cleared the fence?
It didn't clear the fence.
Or how do you know that it didn't?
Okay, Tess, look. Here's the fence. The fence is 20 feet high and it's 400 feet away. So I graphed my parabola. Now, I didn't know that was 20, but when I used my trace button, this point right here, well, no, this point right here was something comma 19. It was 354, I'm making that up, I think that's what it was, comma 19. So what does that mean? That means when I'm 354 feet away, I'm already down to 19. So when I'm 400 feet away, am I gonna be up at 20? Not unless this is a magic ball that all of a sudden goes back up, right? Because it's already below 20 and it's only 350 feet away. Do you see what I'm saying? Yeah, yeah. Okay, all right, we've got to get going here, guys. 6-3 homework will be due on Thursday. So 6-3 due on Thursday, and now we got to look at 6-4. Real quick introduction to a whole new way of thinking about things. So, this unit, the section I should say, is all about what are called polar coordinates. Okay, and the particular paper that I use is in increments of 15 degrees. Like that all the way around. You are used to graphing, we just did it on our calculators. You are used to graphing in a rectangular system where points are plotted according to a horizontal and a vertical distance. You understand why that's called rectangular? Vertical. Your graph paper is a bunch of rectangles. Every point in the rectangular or Cartesian system, this is called the Cartesian system, is identified as a horizontal and a vertical distance. Okay, from this point, which is called the origin. In a polar system, it is not rectangular, obviously it is circular, and everything emanates from the point called the pole, like the North Pole, that's the pole. Points are identified, I know that's terrible, points are identified in the polar coordinate system, there's a point right there. That point would be 2, 30 degrees. So in other words, points are identified by a distance from the pole and the angle in standard position. So what would this point right here be? That would be 4, 45. Now, a huge difference between rectangular and polar coordinates is this. If I came over to my to my rectangular system and I plotted a point, everybody in the whole wide world, every single one of you, every kid in the school, every person in China, everybody would call that point -2, 1. Because that is the only way to name that point. But if I came over here to my polar system and I plotted, let's say, this point right here, my grid is terrible, that's on the 15 line. Some of you would say 1, 15. Probably most of you would say 1, 15. But could a kid down the hall give a different answer? Yeah. A kid down the hall could say 1, -3, 45. Oh yeah, because how are polar coordinates identified? A distance from the pole, 1, and an angle in standard position. Nobody said the angle had to be positive. Furthermore, 1, 375. Nobody said the angle had to be less than 360. Furthermore, nobody said it had to be degrees. We could do it in radians. So how many ways are there to identify points in the polar plane? Infinitely many. And in some ways that makes things easier, and in some ways it makes it harder. But there are infinitely many ways to do that. Okay, so let's do some problems. Okay, plot 2, 30. My thing is so bad, I'm gonna start over. Okay, so can you plot 2, 30? So 1, 2, 30 degrees right there, that's 2, 30. 5, negative 135. Liam?
Why did you not have to go for how far it is? Because I feel like that'd be easier to read.
Liam? That question, I have no idea. This is just the way we do it. R comma theta. The points are always the R comma theta. And I know when you see the R, you think radius, because that's kind of what it is, but it's really, it's Greek letter rho, and it means the polar distance. But you can think of it as radius, because basically that's what it is. It's how far you are out from the pole. All right, where is 5, negative 135?
Down to the quadrant 3.
So 1, 2, 3, 4, 5, and then this is negative 90, and this is negative 270. So this is negative 135. So right there. Everybody okay with that?
Even negative 180.
Oh, yeah, negative 180. Thank you. Okay, and then, whoa, wait a second. Negative 360. Whoa, we'll have to do that one next time. That's a little tricky.
Does that just go the other
Why am I a little freaked out by that?